All right, ready for a deep dive into something pretty fascinating?
Yeah, let's do it.
Today, we're going to be diving into the future of AI, specifically how it understands what it sees.
Yeah.
Um, we're looking at this research paper, and it's on something called AIM, which stands for Autoregressive Image Models. And this has the potential to be a real game changer.
Absolutely.
Yeah.
So,
I think what's really interesting about AIM is it borrows a page from how we train those large language models.
yeah.
You know, the LLMs,
Yeah.
the ones that are powering things like ChatGPT.
Right. The ones that can like practically write a novel in the time it takes you to go get a cup of coffee.
Exactly.
But instead of words, AM is all about pixels. It's like teaching a computer to see the world the same way that those LLMs learn language.
Exactly. Imagine like showing a computer a picture, pixel by pixel, and it starts to be able to understand like, okay, those pixels, that's an ear, that's probably attached to a head, that shape looks like a fluffy tail.
Hmm.
Oh, this must be a cat. Okay, that makes sense. But how does it actually learn that? Like, what is this autoregressive part of it?
So think of it this way. Imagine like doing a giant jigsaw puzzle, but instead of looking for shapes that fit together, AIM is predicting what the next pixel in the picture should be based on all the pixels that it's already seen.
So it's not just seeing like a jumble of colors. It's learning patterns. It's learning relationships between the pixels. It's like if I see a blue pixel, then a white pixel, then another blue pixel, that's probably the sky. So I bet the next one's going to be blue too.
Exactly. And that's where this gets really interesting, is that a lot of current visual AI models, you know, the ones that are like recognizing faces in your photos or helping self-driving cars navigate, they need tons and tons of labeled data. We're talking thousands, if not millions of images where someone has gone in and said, this is a dog, this is a stop sign, etc.
So it's like those AI models, they have to be like spoon-fed all this information, whereas AIM is more like, just point me to the buffet of pixels, I'll figure it out.
That's a great way to put it. AIM doesn't need all that hand-holding. It can learn from raw, uncurated data, which is a huge deal.
Okay, I'm starting to see why this AIM thing has everybody so excited. But before we go any further, could you explain what you mean by uncurated data and why that's such a big deal?
Sure. So think about it. The internet is full of images. I mean, billions and billions of images.
Oh, yeah.
And most of them aren't neatly labeled in a way that would be useful for, training AI.
It's like the difference between a really carefully organized library and like the inside of my junk drawer. Like there's potential in both,
Yeah.
but one is just way easier to work with.
Exactly. And traditionally, training AI for visual tasks has kind of meant sticking to that library approach. But with AIM, we can finally tap into the potential of that massive, messy junk drawer of data.
Wow, that's incredible. But if AIM doesn't need all that labeled data, what's stopping other researchers from doing the same thing?
Well, training AI on that scale, taking advantage of billions of images, it takes a lot of computing power. It's not something just anyone can do in their garage, you know?
So you need the data and the horsepower to be able to make it work.
Exactly. And as we'll see, it's when you combine those things, that massive data and those powerful models, that AIM's true potential really starts to shine.
Okay, so we're talking about massive data sets here, potentially billions of images. Did the researchers actually achieve that kind of scale with AIM?
They did. They really pushed the limits, experimenting with both the size of the data and the size of the AIM model itself.
When you say the size of an AI model,
Yeah.
we're talking about its parameters, right?
Right.
Like those are the internal settings that get tweaked during the learning process.
Exactly. And with AIM, they took those parameters to a whole new level, scaling up to a model with a staggering 7 billion of them.
7 billion. Wow. That's like, I don't even have an analogy for that. That's just a lot of parameters.
Yeah, it's a mind-boggling number for sure. But what's really remarkable is what happened as they made AIM bigger and fed it more data.
Let me guess.
Huh.
It became sentient and took over the world.
Not quite that dramatic, but you can actually see the results in Figure 1 of the research paper. It shows a clear trend. As they scaled up both the data and the model size, AIM's performance on visual tasks just kept getting better.
Hold on, it didn't plateau. I thought there was usually a limit to how much a model could improve, even with more data.
You'd expect to see diminishing returns at some point, right?
Right.
But with AIM, the researchers didn't find that happening, at least not within the scope of their research.
That's wild. So it's like AIM just keeps getting smarter the more you challenge it.
And that's why this research has created so much buzz. The fact that they didn't see any signs of plateauing, even with that massive 7 billion parameter model, it suggests there's still a lot of room for growth.
So bigger data, bigger model, equals even smarter AIM. But how does it actually stack up against the competition? I mean, it's not like AIM is the only game in town, right? So we've got this pixel predicting powerhouse. It's called AIM, and it just seems to defy expectations.
Yeah.
But how does it actually measure up against other approaches to AI vision?
So one of the major players in recent years has been something called contrastive learning. And instead of predicting the next pixel like AIM does, contrastive learning is all about comparing images.
So it's like saying, these two pictures, they both have fluffy ears and a wet nose, so they must be the same type of animal, a dog.
Exactly. It's about finding those similarities and differences between images. And it's worked surprisingly well for a lot of visual tasks.
Yeah.
However, there's a catch. Contrastive learning, it can get really computationally expensive as you start scaling up the data and the model size.
Because the more images you add, the more comparisons you have to make, and it just kind of snowballs from there.
Precisely. It becomes this game of diminishing returns. You're putting in more and more resources for smaller and smaller improvements.
Whereas AIM just keeps chugging along, happily predicting pixels, no matter how much data you throw at it.
Yeah, that's the beauty of it. And that elegance, it's actually reflected in its design, too. AIM's architecture, it's remarkably straightforward compared to some of these other methods. It doesn't rely on a lot of the complex tricks and workarounds that researchers have had to come up with for other approaches.
So it's like AIM's found a shortcut, like a more elegant solution to the problem of image understanding.
In a way, yeah. But elegance only gets you so far. The real test is how well does it actually perform. And that's where Table 6 in the paper comes in. The researchers, they put AIM through its paces on 15 different benchmarks. These are like standardized tests for AI. We're talking everything from identifying objects in photos to analyzing medical scans.
Okay, cut to the chase. How did AIM do that?
It surpassed expectations, even against some tough competition. For instance, it outperformed some methods that initially seemed quite promising, like MAE.
Remind me again what MAE is all about.
Right. So MAE stands for Masked Autoencoder. And basically, it tries to reconstruct images after parts of them have been masked or hidden. It's a clever technique. But it turns out that AIM's kind of more straightforward approach actually achieved better results on many of these benchmarks.
Wow. So even against some of the more established techniques, AIM is holding its own.
It's even more impressive than that. AIM came close to matching the performance of much more complex models like Dano v2, which is a testament to the power of its elegantly simple approach.
Okay, I'm sold on its performance. But we've talked a lot about how AIM learns. What about its actual design? Are there any unique features that contribute to its success?
One thing that stands out is its use of prefix attention. Most autoregressive models, they predict things in a very linear order, one after the other, but prefix attention, it gives AIM a bit more flexibility.
So instead of looking at a picture like a line of text and just kind of reading it from left to right, AIM can sort of jump around a bit and get the gist of the image.
That's a great way to think about it. And this flexibility seems to help AIM learn more generalizable features from the data.
So what you're saying is AIM isn't just memorizing patterns. It's actually understanding something about the underlying structure of images.
Exactly. And another crucial design choice relates to AIM's internal network. They found that wider networks consistently outperform deeper ones.
Wider as in more connections spreading out horizontally.
Precisely. It's a bit like comparing a sprawling single-story building to a narrow skyscraper. Both have their uses. But for AIM, that wider layout seems to be key for efficient learning and scalability.
Fascinating. It sounds like the researchers really put a lot of thought into optimizing AIM's architecture. But for our listeners who aren't, AI engineers, what does all this technical talk actually mean? Why should they care about a model that can predict the next pixel?
That's the million-dollar question, right? Well, the potential applications of AIM, they're incredibly exciting. Imagine training AIM on massive data sets of, say, medical images. It could help doctors detect diseases earlier and with greater accuracy than ever before.
That's huge. What else?
Think about things like satellite imagery. AIM could analyze vast amounts of data to track deforestation, monitor crops, even predict natural disasters with incredible precision.
It's like giving scientists a superpower. They can suddenly make sense of data on a scale that was previously unimaginable.
And because AIM can learn from uncurated data, it opens up possibilities in fields where labeled data is scarce. Imagine using AIM to analyze historical documents, artwork, archaeological sites. The potential for discovery is enormous.
This is truly groundbreaking. But are there any limitations to AIM that we should be aware of?
Of course. A is not a magic bullet. It's important to remember that it's still early days for this technology. There are limitations to any AI model, and AIM is no exception. Other approaches, like those contrastive learning methods we discussed, might be better suited for specific tasks or situations, especially when dealing with smaller datasets.
So it's all about choosing the right tool for the job.
Exactly. And there's still a lot we don't know about AIM. The researchers themselves acknowledge that there's a lot more to explore. For example, the paper hints at the possibility of extracting even more powerful features from AIM's internal layers, which would lead to even more advanced AI in the future.
It sounds like we're just scratching the surface of what AIM might be capable of. It's like we've opened a door to a whole new world of possibilities.
That's a great way to put it. It's an incredibly exciting time to be following the world of AI.
Well, that's it for our deep dive into AIM. Really appreciate you taking the time to break all of that down for us.
It was my pleasure.
And for our listeners, be sure to check back next time when we'll dive into another exciting development in the world of AI.